In the previous video, I introduced you to the idea of the moment of inertia. The moment of inertia is the resistance of an object to change in its rotational motion. We saw that the moment of inertia depends both on the mass of the object and the distribution of mass within the object. In this video, I'm going to show you the formula that we use to calculate moment of inertia for a collection of point masses. We're going to see that the formula incorporates both how much mass we are dealing with and also how the mass is distributed. Here's how we do this. To start, let's suppose that we have here a massless plate. Because the plate has no mass, the plate does not contribute to the moment of inertia of the system. The massless plate is just here to hold everything together. Anyway, the massless plate can rotate on the axle here, and you can see that we have kind of glued or somehow stuck these different point masses onto the massless plate. Mass 1 is a distance r1 from the axle, mass 2 is a distance r2 from the axle, mass 3 is a distance r3 from the axle. So what we're going to do is we're going to start to spin the massless plate around the axle, and when we do that, mass 1 will trace out a circle of radius r1, mass 2 traces out a circle of radius r2, and so forth. So now we have the system that consists of the massless plate and the three masses we have stuck onto it. And we ask, what is the moment of inertia of this system for rotation around this axle here? So here's the formula. First of all, the symbol we use to indicate moment of inertia is a capital I. And for the system here, the moment of inertia would be mass 1 times r1 squared plus mass 2 times r2 squared plus mass 3 times r3 squared. As we saw in the demos in the previous videos, having the masses further from the center of rotation makes it more difficult to change the rotational motion of the object. That idea is reflected in the formula here, because you can see that for each point mass, the moment of inertia increases with the square of the distance between the mass and the center of rotation. Now that I've introduced you to the moment of inertia, we're going to do an example problem, which is really just a straight substitution into the formula that I showed you. So here's the idea. We're going to say that we have a funny sort of a barbell here. That barbell has a 2 kilogram mass at one end, a 3 kilogram mass at the other end, and the barbell rotates around the axle that I have indicated here. If I set the barbell into rotation, the barbell is going to rotate around the axle just like that. As I said, this is pretty much just a straight substitution problem, but why don't you try this yourself? Why don't you just take the numbers that I've given you here and plug into the formula and see if you can work out the moment of inertia of this system with respect to rotation around the axle here. Once you've given that a shot, rejoin the video and you can see what I do. In this problem, we have just two masses instead of three, so we can take moment of inertia equals m1 r1 squared plus m2 r2 squared. We can then substitute. Mass 1 is 2 kilograms. The distance from mass 1 to the axle is 20 centimeters, but I'm going to convert that to meters. So we have 0.20 meters squared. Then we have mass 2, 3 kilograms. The distance of mass 2 from the axle is 30 centimeters. So I'm going to convert that to meters as well. 0.30 meters squared. Then just stick everything into your calculator. I think you'll get 0.35 as the numerical value, and then the unit is just what it looks like, kilograms times meters squared. And now you have seen the formula for moment of inertia, and we have used it in this simple example problem.